Bismillah, wassalatu wassalam ala rasulullah. So welcome to the class, Support Vector Machine. This is one of the recently proposed method and really very powerful algorithm. From my experience, it is an algorithm to beat. I've personally deployed it in several areas with very, very excellent outcome, actually. So it's been used enormously in several fields and has always proven itself to be really, really very powerful. And it's one of the algorithms that personally have deployed it for a lot of applications. See, now, we're going to talk about what is support vector machine, how does it work, how to tune the parameter and type of SVM, then the challenges, the pros and cons, and then now these are a couple of notation that we are going to be dealing with. So as we move along. So we talk of input space, where is containing this, output space, you have the Y, you all know this. If it is classification problem, you have -1 and 1. So we have hypothesis function H containing the big H. We have the real value also. In case of regression problem, the training set could be a set of X1 and Y. The training set is a combination of both input and the output. And then we call something the testing error, which we call the by design. Now, we say that SVM, support vector machine, is a relatively new classification method for both linear and nonlinear data. See? So it uses nonlinear mapping to transform the original training data into higher dimension. This is the big secret of this very wonderful method. The big secret. It has ability to use nonlinear mapping to change the original data to another level where it become transferable, classifiable. With the new dimension, it searches for the linear optimal separating hyperplane, which is the decision boundary. It is one of the classification algorithms we call discriminant algorithm. It tries to draw a line between two classes. It tries to always draw a line between two classes. That is the belief of support vector machine. It believes that every system can be divided into two by a line. If we cannot separate you into a line by a line, I will do something for you, you will become separable. We will discuss this when we get to nonlinear SVM. Now, with an appropriate nonlinear mapping to a sufficiently high dimension, data from two classes can always be separated by hyperplane. So we then find the hyperplane using the support vector, which is essentially training tuples and margin that are defined by the support vectors, as we are going to see. Historical perspective. We say Vapnik and colleagues, groundbreaking work in the statistical learning theory in the 1960s. So they brought this idea that, okay, statistical learning theory, can we do something different? So they talk about, okay, they came up with this idea. You always see Vapnik, so and his colleagues, they were the one that introduced support vector machine. Some of the characteristics or features, characteristics, is that the training can be slow, but accuracy is high, owing to the ability to model complex nonlinear decision boundary. We call them margin maximization. Do support vector machine will take your time, but you are likely going to get better results. So it is used for classification and numeric prediction. It can do both classification and numeric prediction. But then the numeric prediction problem is known as SVR. They call it support vector regression. Some people call it support vector machine also. Support vector machine is one for classification, but the one for regression, they call it SVR, support vector regression. But some people still call the two SVM, which is fine. So it has found its application in several areas, object recognition, speaker identification, and also for other things. Now, support vector machine says a technique used for classification, regression, and outlier detection. See, it can also be used for unsupervised learning. which we are going to consider as the last topic. After this topic, we are going to talk about unsupervised learning briefly, inshallah, to introduce you to it. So in that case, we call it support vector clustering. See, when we do have output, the output is missing. So we use unsupervised learning to solve the problem. So nuclear samples that are mapped into the space, to the same space, can then be categorized based on which side of the gap they fall. The idea of support vector matching is there's always going to be a line. You give me some data, I can only draw a line between the data. So I said it is called discriminative classifier because it takes this training data and then it will get the output of an optimal hyperplane, which we categorize into new examples. So the goal is always to find the optimal separating hyperplane, which maximizes the margin. So how can we maximize our margin? We're going to see an example now. Now, look at this. In two-dimensional space, this hyperplane is a line that divides the plane into two parts, where each class lay in other side. Look at the data you gave to me, Shabab. If I want to classify this data, I just draw a line between them. So once I draw this line, so when new samples are coming, if you're in this side, then you belong to this class. If you're in this class, you belong to this class. You see? So this is the secret of support vector matching. And it's so powerful, so powerful. If you check up some of our publications, you can check up my ResearchGate, you can check up my Google Scholar, you see some of my work, especially when the data set is very few, you go for support vector machine, it still gives you excellent results. The secret is it always tries to draw. Originally, support vector machine was made for classification. Let me mention this. It was made for classification problem. Then later, they extended it to be able to solve regression problem. And another thing you have to notice, support vector machine can only solve binary classification problem because it works on the principle of drawing a line between two classes. And there's no way you can draw one single line between three classes. It's not possible. So you can only use support vector machine for binary classification problem. However, because of demands, there's a way to use it to solve multi-class problem in an indirect way, in which case you have to solve them separately. You have to break the problem into two classes. I have class A, B, C. I can solve for AB, I can solve for BC, I can solve for AC. You cannot solve ABC at the same time in support vector machine. That is the limitation of support vector machine. Like I used to say, everything that has advantages also has its own disadvantages. But then we try to take advantage and try to look for how can we avoid the mistake or reduce it. This is very important for us to take notes. Now, so we say one D data set is a single point, represent the hyperplane. 2D data set is a line, which is the hyperplane, and 3D data set is an hyperplane. 3D data set, it plays an hyperplane. That is everything we always want. So when you have this class, we draw a line like this. So it's separated. So this is one class, this is another class. Now, look at it. We continue. The red and the green, and our data has two features, X and Y. You see, you have two features, X and Y. So we plot them on the plane, on this particular feature space. So we want to classify, given a pair X, Y, we want to know where it belongs to. So support vector machine will take this data and then generate a separation for them because we know where this data belongs to. It generates a line for them, a decision boundary. This line is called the decision boundary. See, once we are able to draw this decision boundary, it separates it automatically. So SVM bases its idea from what we call the computational learning theory. So and the advantage of it is that it has this characteristic that it is optimally defined. It is an optimally defined surface. typically non-linear in the input space and linear in higher dimensional space. See, this is the secret. If I have data like this, these are different classes mixed together. I cannot draw line between 0 and these ones now. There's nothing way I can do it. So I push it to higher dimensional space. At higher dimensional spaces, it becomes separable. This is the secret of support vector machine. We'll come back to that, inshallah. Now, so it's implicitly defined by the kernel function. There's a kernel function that's going to help us to push to higher dimensional space. There are two independent developments within the last decades: the concept of computational learning theory and new efficient representation of nonlinear function that uses kernel, which we call kernel function. So, and the resulting learning algorithm is an optimization algorithm rather than a greedy search. Support vector machine is not a greedy search. It is an optimization algorithm with a lot of mathematical background. That's why some people don't like support vector machine. It has strong mathematical background. It solves quadratic equations and try to use to optimize some of these equations. The next is, how do we identify the hyperplane? I've told you that support vector machine work by separating using an hyperplane. This is the hyperplane. How do you do that? Now let's listen now. +1 represents X, -1 represents 0, you know, when you want to predict. This is a classification problem. Now, so we build a hyperplane. You try to put this one in. The idea is, Shabab, if I have to draw a line between this guy, I can draw it this way. I can draw another line like this. I can draw it this way. There are so many ways I can draw this line, Shabab. So, but the idea is, which one is going to be the best? So once you draw your line, you try to increase this size. There's a center at the margin, we call it. You need try to increase the distance between this and this place. Increase it, keep increasing. You keep increasing until you touch one sample from this side, or you touch one sample on this side. I touch one sample here, then I'm going to stop. This line with the maximum margin is the one I'm going to select. So if I choose this line, if I choose to separate using this line, I might not be able to get maximum margin for it. So I choose the one that will give me the maximum margin. So this line at the center is known as the hyperplane that we have drawn. Then the line I've created is the margin. So you keep pushing the margin away until it touches one sample from each side, or at least one sample, not one sample every day. You can touch as many as possible. These samples you are touching on both sides, we call them support vectors. And that is why we get the name of this learning algorithm, support vector machine, because these are the guys that will do the work later. They're going to behave like nearest neighbor now. So once I catch my support vector, I know this is support vector for this class. It means any data that falls closer to these guys, they're going to be in this class. Any data that falls into this side, they're going to be in this class. But to identify your support vector is very challenging. You can see in this side, we only have one support vector. But here, you have two support vectors. It is not by your doing. It is the maximum margin. If you choose this line, you might not be able to get the maximum margin. If you choose the other line, you will not be able to. But this is the one that gave us the maximum margin. We'll come back to that. We say a hyperplane is a linear decision surface that splits the space into two parts in binary classifier. So this is the hyperplane. This line at the middle is separate them into two parts. Anything to this side is this class positive. This one is negative. So the idea is that there will never be any data point inside the margin. It is assumed that there will not be data inside the margin. Even though we are going to discuss it later, there are special cases where we may have to allow it. Now, how does it work? One, identify the right hyperplane. This is the first step. The rule one is to select the hyperplane which segregate the two classes better. That is, what is the hyperplane that segregates the class better? There could be several possibilities. Then two, you try to maximize the distance between the nearest data point of either class. See, first of all, select the best hyperplane that can segregate them more. Now, let's look at the possibility. See, imagine it's a separation of line to the closest class point. Look at this one. I draw a line now. You can see that, look at the distance between this line and another side. You can see it has a distance. Equidistant as far as possible for both sides. You can see that there's a little bit of equal distance from this side and this side. This is a good hyperplane, a good separating line. So we now try to maximize, once we select the best one, we now try to maximize it so that we now say, okay, these are the support vector. These guys are the support vectors. We got only one support vector here, or what happened. Now, this is a bad margin. This is a good margin. This is a bad margin. When you draw your line, it is far away from this class, but too close to this class. This is not a good margin to draw. So you want something in between the two classes. See, that is why we say step one, select the hyperplane which separate the two classes better. That's why you have to draw many possibilities. Is it this one? Is it this one? Is it this one? And then you calculate the margin of separation. Now, the margin is the perpendicular distance between the closest data point and the hyperplane. After you have drawn the hyperplane at the center, so you try to push the margin backward until it touches the data, which I've shown to you. Until you start touching this one, which we call support vectors. That is the margin. The difference between hyperplane and the margin. Hyperplane is the first line that you draw. You check it. Is it equidistant from both sides? Yes. Then you try to increase, you now create another margin for it. Until I touch a value here, this support vector. You draw this one here also. This is the margin. I've created a margin. The distance between these places is known as a margin. Now, so the best optimized line or hyperplane with maximum margin is termed as the margin maxima hyperplane. And the closest point where the margin distance is calculated are considered as the support vectors. So these are the guy that is sitting on that particular margin that we have drawn. For positive class, this guy is going to be responsible. This is predict class, negative class zone. This line is going to have WS plus B is equal to 0, line equation. While this one is going to be WX plus B is equal to -1 because of the class. While this one is representing +1. So this is how support vector machine grows. How do you classify this? You see, this is a possibility. We can draw the line like this. But this line, you can see that this line is not providing us with what we want because it's too close to this guy. It's far away from this guy. So we will not use this guy. I draw another one. This one is too close to this guy. It's too far from the other guy. I might not use this. So finally, I'm able to draw one. Look at this one. It is both far away from both sides. So I now try to push them back. I try to create the hyperplane until it touches one here and touches one or more here. It can touch it more, but there's nobody on the line here. Because I'm more concerned with the margin. I don't care the number of samples it touches here, but at least it must touch one before you stop pushing. So we find out, oh, this is maximum margin. And they must be equidistant. The distance here is equal to the distance here. This is the idea. Those points are known as support vector. So you define the margin of a linear classifier as the way that the boundary could be increased before hitting a data point. What is the margin that I can increase this guy before it starts hitting the data point? So this example of a linear function to separate two classes, which is given in this mathematical expression. Now, so the maximum margin has been created. This is what we call the maximum margin linear classifier is the linear classifier with the maximum margin. This is what we call LSVM. LSVM, you see in some places, they call it LSVM. It means linear support vector machine. It works on problems that are linearly separable. The original problem is separate, you can easily separate it. No issue. So these are the support vector. These points are the support vector. The points that are on the marginal pushes of the up against. So now, if I now have a new class, and this one falls here, we don't care about this guy in our training set. This is a misclassification. We may classify to +1. It means the data is not falling with his colleagues. So we don't, because of this guy now, say, okay, we're going to suspend our, no. So maybe in my training, I'm getting 98% accuracy, which is fantastic. See? So what we're saying is data separation is not perfect. It tolerates some outliers in the classification. That is support vector machine. Sometimes you might have data that is falling in the wrong side. It's okay. We let it go. But majority must be in the appropriate side. Like I always tell you, training set, it's not for you to get 100% accuracy in the training set, but no, you want to get reasonable result in training set so that you can get better result in the other side. That is linear classifier. So we are going to call it a stop here today. The time is gone. So Shabab, take note of this page 17. We're going to start from here next week, inshallah. And then, so Barakallah Fiqh. I wish you all the best in your final exams.